Welcome to this explainer. Today, we're doing a definitive architectural design review for building and, more importantly, scaling production-ready agentic systems. We're zeroing in on strategies for deploying open-weight models, pulling everything directly from the recent deep dive into the Gemma 4 family. So if you're an architect or a senior engineer tasked with orchestrating these autonomous workflows, integrating local hardware, or securely connecting massive reasoning models to your enterprise data, you are absolutely in the right place. We're going to break down exactly how to implement agentic workflows using Gemma 4 with a really heavy focus on local versus cloud deployment and some pretty fascinating data integration patterns. Here is our roadmap for today. First, the Gemma 4 compute layer. Then, infrastructure topology. Number 3 is the data integration layer. Fourth, local and hybrid routing. And finally, we'll wrap it all up with parallel execution. All right, section 1, the Gemma 4 compute layer, selecting the right engine for the workload. Okay, let's dive into this. When you're designing any agentic system, your base model is your foundational solution, right? And the Gemma 4 models now come with native function calling and reasoning built right in, which is a huge deal. Looking at the model selection matrix, you've really got to select the right engine for the specific workload. For edge and IoT devices, that 2 billion parameter model is your go-to. Moving up to high-end phones and laptops, you've got the 4 billion parameter option. But for server-grade, massive enterprise applications, you're faced with an architectural choice. Do you go with the 26 billion parameter mixture of experts model, which is highly optimized for runtime speed, or the 31 billion parameter dense model? That one is your absolute powerhouse for deep reasoning and fine-tuning. And crucially, Google actually moved this entire family over to an Apache 2.0 license, which means you have complete, unfettered control over your commercial pipelines. Now, that brings us to a massive and honestly critical number, 256,000. That is the token context window size for both the 26B and 31B models. Look, in the agentic era, having a massive context window is not just a nice to have anymore. It's a hard requirement. When your autonomous agents are out there executing multi-step plans, holding state across a long conversation, referencing massive API docs, or analyzing really complex database schemas on the fly, they absolutely need the memory capacity to hold all that context simultaneously without losing the thread of what they're actually trying to do. Moving on to Section 2, Infrastructure Topology. Evaluating cloud deployment architectures. Now, what's really interesting about this slide is how you evaluate your cloud deployment once you've picked your compute engine. You have to weigh billing and deployment trade-offs right out of the gate on the Gemini Enterprise Agent platform. On one hand, you've got Model Garden. Think of this as a one-click deployment where you provision specific, heavy-duty hardware like H100s or RTX 6000s, and you pay for that dedicated endpoint to be online 24/7. It's yours. On the flip side, you have the serverless API approach. Here, the model is essentially provided as a service. You just call the API and pay per token processed. If your traffic is super variable or if you're just prototyping, serverless is incredibly cost-effective. But for sustained massive throughput, holding a dedicated endpoint is definitely the better architectural choice. Now, for those of you who want more hands-on control over your infrastructure, you're looking at another fork in the road, GKE versus Cloud Run. With Google Kubernetes Engine, you get total control over the raw virtual machines and GPUs. You can tweak literally every single configuration knob, but, as we all know, that comes with the joy of managing all that Kubernetes overhead. Contrast that with Cloud Run. Cloud Run is all about developer velocity. You can deploy Gemma with just 2 lines of code. It auto-scales up to handle massive spikes in requests, and beautifully, it scales all the way to 0. So if your server goes to sleep from inactivity, it just warms right back up in a couple of seconds. Which brings us to Section 3, the data integration layer. Database integration using MCP servers. Let's be real, an agent is completely useless without data, and that brings us to MCP server integration. In the source material, they demonstrated this by pointing an agent development kit running Gemma 31B toward a BigQuery MCP server. Configuring this basically means having the MCP server expose the database schema and the query execution endpoints as standardized JSON RPC tools. So the MCP server acts like a secure bridge. It translates the model's function calls into actual, safe database queries for a system that the model inherently knows nothing about. The architectural case study they used here was a live city bike database tracking local bike demand in real time. Let's walk through the exact agentic loop we observed because it's pretty wild. When prompted to optimize revenue, the agent didn't just guess. Step 1, it autonomously queried the database just to understand the schema and see what data was even available. Step 2, it actually devised a multi-step optimization plan. Step 3, it executed queries to run experiments. And finally, step 4, it output the top 10 locations to improve service. And all of this happened at real-time speed over just 3 minutes, entirely driven by the 31B model's reasoning engine. But the absolute most crucial point is embedded right here in this quote from the presentation. It makes a mistake when it tries to join two tables. It can fix this all by itself. There is no other user turn. Just like any human developer, the agent actually wrote a bad SQL join. It had a typo. But instead of just crashing and burning, it received the error back from the database, realized its mistake, rewrote the query, and kept going. That is the holy grail of multi-step planning and tool use. True autonomous task completion with zero human intervention after that initial prompt.
Section 4, Local and Hybrid Routing, System Resilience and Failover.
Look, not every workflow lives exclusively in the cloud. Building agent features for mobile poses a really unique challenge. What happens if the phone is too old or just lacks the memory to run the model locally? The failover pattern showcased uses Firebase AI logic. You prioritize a local execution attempt first, using something like AI Core on Android. But if the local hardware is insufficient or just unavailable, the system gracefully and automatically routes that exact same query up to your cloud server endpoint. This guarantees system resilience and a totally seamless user experience. And the best part is, the developer doesn't have to manually hardcode all that complex fallback logic. So why is this hybrid architecture so highly valued by engineering teams? Zero ongoing server costs for local execution. By pushing these agentic workflows down to the device level whenever you possibly can, you drastically reduce your cloud compute spend. And at the same time, you're offering users incredibly low latency and even offline capabilities. You are literally only paying for cloud compute when the local device simply can't handle the task. It's a massive win-win.
Let's move to and see how this builds. Section 5, Parallel Execution, Scaling Concurrent Local Agents.
We've spent a lot of time talking about a single agent. But what happens when you need localized pools of agents for concurrent execution? To achieve this locally, developers are leveraging OpenAI-compatible local endpoints. By spinning up local inference servers like Llama CPP or LLM Studio, you can actually map the model's interface directly to your local host. This means that existing agent frameworks, ones that were designed for cloud APIs, can instantly point at your local machine. It enables lightning-fast orchestration of local Gemma agents. The impact of this parallelization is profound. The sources highlighted several brilliant examples. First up, there was AI Venture. It's this open-source dungeon crawler where a local Gemma agent literally vibe codes HTML, CSS, and JavaScript on the fly to build the game while you're playing it. Next, concurrency. Imagine an orchestrator delegating a design task to 15 separate local agents, generating SVGs simultaneously on a single laptop just to maximize throughput. Insane. They even showed polyglot coding, where 8 concurrent agents independently wrote solutions in Rust, Python, and JavaScript. By providing custom tools to the orchestrator, your local agents gain the exact specific skills they need to navigate your unique codebase. So we've covered the model selection matrix, the cloud deployment trade-offs, MCP database configuration, hybrid failover routing, and localized parallel execution, the tools to build highly resilient, deeply integrated agentic systems. They are entirely open and available right now. So the only question left for you as an architect is this: how will you architect your autonomous future? Take these deployment strategies, take these integration patterns back to your production systems, and start building. Thanks so much for joining me on this explainer, and I will catch you on the next one.